In this 3 steps to sketch, we're going to graph a shifted cosecant equation, y equals 2 cosecant of pi over 2x plus pi over 2 plus 2. Now, just looking at this equation, you should be able to recognize some of the shifts that we see. This plus pi over 2 is a horizontal or phase shift, and then this plus 2 is a vertical shift. And that's how we know we should be analyzing and using our method for shifted cosecant graphs. So let's go ahead and get started. Okay, here's our method outline. And before we dig into discussing the method, know that this method really relies on your knowledge of being able to graph shifted sine graphs. And likely if you're trying to graph cosecant graphs, you already know sine graphs. And so you'll see that most of this method is just what you will already know from graphing sine, with one small change in step 3, where we actually create the reciprocal graph or the cosecant graph. If you aren't yet familiar with how to graph sine graphs, I highly recommend going and watching some videos on that. I'll put links in the video description because that just makes this whole process much easier. All right, so in step 1, we're going to find our companion equation. Basically, you'll just take your equation and replace the cosecant with sine, and then you'll analyze all the essential information for that. So you do a lot of the bulk of the work here. You'll also find the asymptotes equation in this step, and that'll be the asymptotes for your final cosecant graph. In step 2, you'll plot your companion pattern and then shift it. You'll do this lightly or in a separate color from your final graph. And then in step 3, from that intermediate companion shifted graph, you'll create the reciprocal graph. So there are some quick little transformations that you do, and then you'll have one cycle, you'll sketch it in, one cycle of cosecant. Then you'll repeat, and you'll have a great little sketch. So let's jump in. Here's our equation again. And I'm going to write out the general form for a shifted cosecant graph just so we are familiar with where all of the information is coming from. So y equals a cosecant of bx minus c plus d. Okay, so that'll help with some labeling. And one thing I like to go ahead and point out before we jump into the method is this bx minus c part. So bx minus c is the format for your general form. And notice that our equation is close to that form, but we actually have bx plus c. So the sign or the value for the c is actually disguised a little bit. You may like to think about this, and I'm just going to write this part out to the side, as pi over 2x minus negative pi over 2. Okay, so your value for c is actually negative pi over 2. And that's really going to be important when we talk about our shifting a little bit later on. So this will be movement to the left. Okay, and I think that just can be a common mistake, so I like to go ahead and address it up front. All right, so let's write out our companion equation. Again, we just replaced cosecant with sine because we're really relying on a lot of our graphing knowledge for sine. So we have 2 sine pi over 2x plus pi over 2, and then plus 2. All right, starting off analyzing the base graph pattern. We know a is the coefficient in front of sine or cosecant, so that's a 2. Okay, that tells us our amplitude for our sine function, or distance from midline to max or min. That a is going to be helpful for us when we plot our companion pattern max and min. Okay, so we'll come back to that. B is the coefficient of x, so that's pi over 2. All right, so B tells us how many cycles of our graph we should have between 0 and 2 pi. So as a nice estimate, just calculate 3.14 divided by 2. We know that's about 1.57. So really you're going to have 1.5 cycles or so, a little bit more than that, happening between 0 and 2 pi. And that's just a nice thing to kind of double check once you have your final graph. All right, B also helps us find the period or the length of one horizontal cycle. And we do that using the formula 2 pi divided by B. So we have 2 pi divided by pi over 2. So let's actually multiply by the reciprocal. Simplifying that, we see the period should be 4. All right, now we're ready to choose our scale labels. And I like to be really intentional about how I set the horizontal scale, or how we're going to label each tick mark. Take the period and divide it by 4. And I do this because in step 2, when you plot the companion pattern, it's a lot easier if your first intermediate graph aligns with each horizontal tick mark. All right, so of course 4 divided by 4 is 1. So we'll count by 1 for our horizontal scale. And for our vertical axis, 1 usually works really well. Look to that a value just to do a double check, but that'll work really well here. So let's quickly get our grid labeled. Easy enough, we're counting by 1s for each axis. So you may just label like this real quick, pause if you need to, but we've got some good labels here. All right, now we're ready to talk about our shifts. So to find our shift for our horizontal shift or our phase shift, you do C over B. Okay, so remember we talked about C when we first started our analysis. Because we had this plus sign in our equation, we need to think of that as minus a negative. So the value for C is actually negative pi over 2. And then, of course, B is pi over 2. So again, dividing by that fraction means we're multiplying by the reciprocal. Okay, so that's going to simplify to negative 1. So we have a shift of left 1 unit. Okay, if it helps you to write out left, do that. But that is our phase or horizontal shift. Now, D is going to be our vertical shift, that plus 2 at the end of the equation. So that means we're going to shift up 2 units. All right, the last big piece of analysis is finding the asymptotes equation. Now, there's a really good way that you can do this for any cosecant equation, and it's really applying the horizontal transformations of your equation to the parent asymptotes, or the asymptotes that would happen for cosecant x. Okay, so to do that, take your inputs from your equation. So inputs are, and I'm going to do scratch work right here, pi over 2x plus pi over 2, and we're going to set them equal to the equation for those parent asymptotes. So those asymptotes happen at 0 plus pi k. Pull up that graph if you aren't familiar with it, cosecant x, and you'll see that this is the case. Remember, k is just representing an integer, and we'll talk a little bit more about that in a minute. So now we just need to solve for x, and this will be our asymptotes equation. So subtract pi over 2 from both sides, and pi over 2 is only going to be combining with that 0. It's not like terms with pi k. So now we have pi over 2x on the left equals negative pi over 2 plus pi k. And then we're going to divide both sides by pi over 2. Or if you want to, just multiply every term by 2 over pi. That's the same thing. And on the left side, we have x equals, so 2 over pi times pi over 2. Of course, that gives us negative 1. Of course, there's that negative there that I didn't say. And then when you do 2 over pi times pi k, you get plus 2k. So our asymptotes equation is x equals negative 1 plus 2k. I like to go ahead and sub in a few integers for k here, so that when I'm graphing my final graph in step 3, I can double check those asymptotes. So let k equal 0. We should expect a final asymptote at x equals negative 1. If you substitute in 1 for k, you'll get an asymptote at x equals 1. Substitute in negative 1 for k, you're going to end up with an asymptote at x equals negative 3. Okay, so that's just 3 of our asymptotes, but it's a really efficient way to represent all the asymptotes for our equation. All right, so we're done with our analysis for the most part here. We're ready for step 2. We're going to plot our companion pattern and then shift it. So do this lightly or in a different color. I'm going to use light blue. And let's recall that our companion pattern, our base pattern for a sine graph, is starting at the origin with a 0 or an x-intercept, up to a maximum, to another x-intercept, then to a minimum. Okay, and we will go ahead and start this on our graph. So mark lightly, starting at the origin, your first x-intercept. Our maximum, remember these are going to align with each of the horizontal tick marks because we designed it that way when we set our horizontal scale. So at the first horizontal tick mark, we'll put a maximum, and the y-coordinate comes from the a value, so it'll be 2. All right, move to the next horizontal tick mark to the right. That's an x-intercept. Move again, and this time we'll have a minimum, so its y-coordinate's just going to be the opposite value of a. All right, so hopefully you can roughly see a sine curve there. And now we're going to go ahead and apply the shifts. So I'll mark this next intermediate graph with x's in the same color. So starting at the point on the origin, we're going to do both shifts at once because I think we can handle that. Moving left 1, which is 1 grid unit, and then up 2 vertical grid units. It's a nice scale we have here. So move left 1, up 2. Here's our next point. Take the maximum, move it left 1, up 2. The second x-intercept, left 1, up 2, marking over that original point, and then the minimum, left 1, up 2. So again, you can see I'll sketch in this shifted sine curve here. Okay, and now we're ready for step 3, where we sort of transition this into the reciprocal graph. So I'm going to use green here for our first cycle of our final cosecant graph. So each of what were the original x-intercepts before we shifted, so they're now the ones with the y values of 2, those are going to turn into vertical asymptotes. So here, that original x-intercept now becomes a vertical asymptote. You can kind of remember that by thinking, okay, well, of course, an x-intercept has a value of 0, and if you try to take the reciprocal of 0, you have 1 over 0. That's undefined, thus that's where the vertical asymptote comes into play. All right, the maximum from our companion sine curve becomes a local minimum for the cosecant graph. Okay, so I'm going to go ahead and sketch in the cosecant curve too. Okay, so here's that part. And then the minimum from the companion sine graph becomes a local maximum. Okay, so it'll look a little bit like that. So there you have one cycle of our final graph. Do notice that 2 of the asymptotes that we had discussed from the asymptotes equation are holding true. So we said when k was 0, we got an asymptote at x equals -1. And when k is equal to 1, we got that asymptote at x equals 1. So now let's just repeat this pattern for as many cycles as we have room for. So we'll have a vertical asymptote here at 3. I'm sure you're thinking, hey, that's when k equals 2. That's exactly right. We have a local minimum and another vertical asymptote at x equals 5. And that's when k is 3. All right, working back in the other direction, we'll have a local maximum here, a vertical asymptote at -3, and of course that's what we talked about when k is equal to -1. We have another local minimum and another vertical asymptote. We have room for that. And you're probably thinking that's when k equals -2, and you're exactly right. So here we have, what is this, 2.5 cycles of our graph, a really nice sketch of it. Hopefully this helps you understand the 3 steps to sketch method for shifted cosecant graphs really well. I will post some links to playlists with a lot more worked examples of cosecant graphs, as well as all the other trig functions. So check those out if you're interested. And thanks so much for watching.